All right, I'm going to look at a theorem that pertains to modular arithmetic. And this particular theorem says that if we have integers a, b, c, and m, where m must strictly be larger than 0, and we define d as the greatest common divisor of the integers c and m, and also that we have some product that is congruent to another product under the modulus m, then it should also be true that the terms a and b, if we essentially have this cancellation of the c's, will be congruent to each other mod a new modulus term, which is going to be the original term divided by this common divisor. So I have a few numbers up here to see if we can show that this theorem actually holds. We're going to let d be 5, c be 10, m be 15, a be 2, and b is going to be 8. And we're going to see if this works. So 2 times 10 is going to be 20. That is my a and c terms. So I have 2 and 10 here. And so I have 20. Now I'm going to do this mod 15 because I've defined m in my specific example as 15. So 20 mod 15 is congruent to 5. Now I want to check the next one. I want b times c. B, I've let be 8 in this instance. 10 again is c. And so 8 times 10 is 80. So we want to look at 80 mod 15. And hopefully we will find that that is also 5. It's congruent to 5. And so we have that this statement is true. The products of a and c and b and c are going to be congruent to each other under this modulus. So now let's look at the original a and b. Is it true that 2 is congruent to 8 under the new modulus, which is m divided by d? So we have m is 15, d is 5, and so when we divide those, we get 3. So looking at 2 mod 3, that is 2, and then 8 mod 3. Looking at 3 divided into 8, we find that we can do that 2 times and get 6. 8 minus 6 is 2. The remainder is 2. And so it is true that 2 is congruent to 8 mod 3. So we have checked this theorem using a set of real integers. So we can demonstrate that this is true in a specific case. All right, we're going to look at the proof for this theorem. I'm going to let c equal d times k, and m is going to equal d times h, where k and h are both integers, and h cannot be 0. The reason h can't be 0 is because of this restriction of m having to be greater than 0. If h were 0, that would make m 0. And we know that d is a factor of both c and m because it is the greatest common divisor. And now we're going to put that into this piece here. And so we're going to rewrite this with our new terms. So a times d times k is going to be congruent to b times d times k, and all of that is going to be mod d times h. So establishing these factors and then substituting it into this piece, I have this statement. Now what I want to do is I want to go through and remove the common factor. We have a common factor here, here, and here of d. And the modulus removes those common factors anyway. So we're going to go ahead and do that. So if I remove d from here, here, and here, we're going to have a k is defined as b is congruent to bk, and that will be mod h. So now, by definition of what the modular arithmetic does, we have that h must divide ak minus bk. And factoring this piece here, we see that we can take out the common k and have a minus b. So h divides this thing, which means that h divides k or h divides a minus b. But h can't divide k. Why can't h divide k? H can't divide k because d was the greatest common divisor here. So k was a factor of c. So if k is a factor of c, then that means that d wouldn't have been the greatest common divisor. So this is not a possibility. That leaves us with h dividing b, or a minus b. So by definition again, we're going to use the definition in the reverse order. Since h divides a minus b, then a must be congruent to b mod h. But what was h? H is m divided by d. If we look at this, if I divide both sides by d to get h, I have h is equal to m divided by d. So a is congruent to b mod m divided by d, which is what we were trying to prove. And so that'll conclude our proof. Cheerful calculations.